the topic today is buckling, and for buckling, we want to see how the structure behave under the compressive axial load. What are the structures that have a compressive axial load? For example, we talking about the column in the house. For the column, they carry the load from the roof, go down vertically, the weight of the roof go down to the column, and that create a compressive stress on that member. For that member, when we design, we need to consider the buckling. So what's a buckling? I will demonstrate next. With a demonstration of one example that called column. So let's define a general term, what is column in mechanics of material, column. So basically, it's a structural member, structural member that subjected to a compressive axial load, subjective to a compressive axial load, and that we call it column. And let's give one example of the column here. With the column, and for example, top is a pin support, and the bottom is a roller support. And then if we have that member is in compression, so we have the applied load go to through the axial axis of the member or longitudinal axis and get into the member, tend to compress the member, and that member we call it columns. And with that time of load, for that time of structure, which is column, there is one failure that we call it buckling. So let's define buckling. What is buckling? So it's a lateral deflection, of a column, or basically any member that have a compressive axial loading. For example, in the truss member that in compression, so that member also tend to have buckling, and when we design, we also need to consider buckling. So let's see one example. I show you what is the buckling in one column with have a lateral deflection in the demonstration next. You see an example of buckling. So we have a cow member, but the load is in compression. So it means that if I apply the load vertically going down in this column, and as you can see, the column will buckle. And in that case, when you design, you have to take care of this, because in the structure, when you design, even the member is not crack or cross, but it buckle like this, it will be unstable, and no one want to live in that building or in that structure. So for the member that in compression, we need to not only design for crossing, we also have to design for the buckling in that example here. And for the member that in tension, it will not be buckled. I show you an example for the member. For example, here, if I apply the load, go out of this member, so it's in tension. So in that tension, you see no buckle. But now if I apply very gentle, compress the member is buckle. So that here, so that you can see it buckling typically only apply for the member that are in compression. With that demonstration of buckling, and to consider buckling, Euler come up with the equation, and let's discuss that equation. And that is Euler Euler-Bucklin equation. So for Euler-Bucklin equation, so we call that either P Euler and for P Euler normally they also that is the critical load. So let's say critical, and that is equal to pi square E modulus of elasticity, Young modulus, I, do you recall what is I? Area moment of inertia, something you could just learn in lesson 4 and worksheet for F and G, over K L square. So that is the Euler-Bucklin equation, pi square E I over KL square. And what is L? Basically that is the length, the geometry length of the column. K, we call it effective length factor. So let's box Euler equation or critical load here for the member subject to buckling, and let's define K. K is the effective length factor, and for that effective length factor K, it measured by equation K equal to effective length, effective length divided by actual length, which is the actual geometry length of the structure. So effective divided by the actual. So what is the effective length factor? It depends on the end condition, support condition at both ends of the columns, and that I will show you another demonstration, and then we come up with different scenarios with different mode of different end condition and how K will be for each end condition. But before we get into demonstration and get into the detail of K with different end condition, let me finish this one with we have the load P critical, and then the also called Euler load. How can we determine the stress? So in terms of stress, in terms of stress, we can have sigma, the normal stress, or due to buckling, so it will call it Euler, due to the Euler P, force P here, or P critical, the critical load, it equal to, as you can see, sigma equal to P over A, so let P critical in that equation divide by the area of the member. So with that, we can have that is pi square E over K L over R square. And what is R in this case? So we can have it where R is not a geometry radius, but here R is the radius of gyration, radius of gyration. If you recall radius of gyration in kinetics, so that one we call it K, lowercase k, but this one, because the K capital we already use for effective length factor, so that you are in this case the radius of gyration, so it does not mean we only apply for the column member will have a circular cross section for any shape. This is the radius of gyration, nothing to do with the geometry radius of a cross section. And from that, what is the radius of gyration in this case? So r equal to I, which is the area moment of inertia divided by the areas. If you go back to the radius of gyration in kinetics, then the k equal to square root of I, mass moment of inertia, divided by mass. But for this one, the radius of gyration measured by square root of I, area moment of inertia over the areas.